Welcome to week 11, question 1. We're looking at multivariable functions, so functions that have more than one variable, and we're going to be finding local extrema. So the first thing you need to do with any function is you're going to be finding the first derivatives, and then you're going to be finding the second derivatives. You're going to be determining whether we have a local extremum or not by finding the m value, and then we're going to find out what kind of extrema we have, whether it's a max or a min, by looking at our second derivatives with respect to xx and yy. So let's have a look at the question. It says here, a company is developing a new soft drink. The cost in dollars to produce a batch of the drink is approximated by this function, where x is the number of kilograms of sugar per batch, and y is the number of grams of flavoring per batch. So it says find the amounts of sugar and flavoring that result in a local minimum cost for a batch. So the first thing we need to do is find the first partial derivatives. So remember, when we're looking at the derivative with respect to x, we're going to consider any y variable. We're going to be considering it a constant. So we have 2200, that's a constant, so the derivative is 0. We have 27x cubed, the derivative there is 81x squared, and then we have minus 72y. 8y squared only has a y in it, so that's considered a constant, and the derivative is 0. So the derivative with respect to y, we are considering any x variable as a constant. So the first two terms are constants, the derivative is 0. Then we have minus 72x, and we have plus 16y. That's the derivative of 8y squared. So you can see that we have a little bit of a different situation than we may have had in the past. We have an x term and an x squared term. And in this case, I think the easiest thing to do is find a function that y is equal to. So first thing we do is set it equal to 0, set each derivative equal to 0. I'm going to draw a line there. So here, if we rearrange the equation for y, we're going to have y equals 81x squared divided by 72. So we're going to have 81 over 72, which is 9 over 8x squared. Here, if we rearrange the equation for y, we're going to have 72x divided by 16, which equals 9 halves, and that's x, 9 halves x. Okay, so now we have two equations that both equal y, so we are going to then assume that if they both equal y, then they must both equal each other. So on the next page, we're going to solve for x. So I've brought the two equations forward from the last page. Y equals 9/8 squared, 8x squared, y equals 9 halves x. And we're going to set each of those equal to each other because they both equal y. So now I have 9/8 x squared is equal to 9 halves x. And I'd like to multiply out the factors, and I see that the denominators 2 and 8, they have a common denominator of 8. We'll get rid of that fraction. So if we multiply through by 8, we have 9x squared is equal to So here we have 9 halves divided by 8, that's 36x. So now we have 9x squared minus 36x equals 0. And I think we can factor out 9x, I guess. We can yes, 9x. So that's x minus 4 is equal to 0. So either 9x equals 0, so x would equal 0, or x minus 4 equals 0, where x is equal to 4. So now we have two values of x, and if we recall from the question, x is the number of kilograms of sugar per batch, and we're trying to make a local soft drink, or a type of soft drink. So if x is kilograms of sugar, you can imagine that a soft drink with 0 kilograms of sugar would probably not taste very good. So given the context, we're going to suggest that x equals 4 is likely the value that we're looking for in order to minimize the cost for the batch. So now we need to find out how many grams of flavoring we need, and we'll do that on the next page. In order to find the value of y, given that we have x values of 0 or 4, you would take one of the partial derivatives and substitute those values of x in. As I said earlier, when x is 0, that means in this case that the number of kilograms of sugar in this new soft drink is 0. So we can just substitute it in just to go through the motions, I guess. So y is equal to 9 halves x, where x is 0. So you can see that y would be also 0. So imagine a soft drink with no sugar and no flavoring. So that isn't a viable value, really. And then let's find what the y value is when x is 4. And that would be 18. So you have 18 grams of flavoring for this soft drink. Now, we still need to prove that it's a minimum. It's an extrema, and specifically is it a minimum. So we're going to need to find the second derivative, partial derivatives, with respect to x again, with respect to y again, and then each with respect to the opposite variable, so an xy second derivative and a yx second derivative. So I'll probably do that on the next page, and I'll pull up the first derivative functions and we'll go through them there. Here are the two first derivatives brought forward to this page. So we have c sub x of xy and c sub y of xy. So now we're going to find the second derivatives. So cxx of xy. So we're going to be considering y is a constant, and so we just have one term here with x in it, so that will be 162x. cyy, sorry, cxy. So now we're looking at the first derivative with respect to x, but we're taking the derivative with respect to y this time. So x is going to be kept constant, so we have a value here of negative 72. Over on this side, cyy of xy. So we have 16, because negative 72x doesn't have a y in it. So we only have one term with y in it, that's 16y. And here we have 16 of cyx. So we're going to be looking at this derivative with respect to x now. So y is kept constant. We have negative 72. And you're going to note that CXY and CYX are the same at negative 72. You'll see that pattern carried through. So the one thing we still have to do is evaluate this second derivative with respect to CXX. We still have a variable in there, and this is somewhat unusual for the questions we've been working on or will be working on. So we need to evaluate this at 0 and 4, so at 4 actually, and we're going to do this, 648. Okay, so we can see that our CYY and CXX, they are both greater than 0, which means that we have a minimum value. If they were less than 0, we would have a maximum. So now let's evaluate M. M, we take the second derivative with respect to XX, second derivative YY, we multiply those together, and we're subtracting the square of CXY. So we have 648 times 16 minus negative 72 squared, and that will give us a value of 5148. So again, this is greater than 0, which means we have an extrema. That's what that tells us. But if we were looking at the second derivatives xx, yy, we know that it's a minimum. And now we need to still find the minimum cost. So let's not forget our end goal. We have to go back to the original equation, substitute the values that we found, which are 4 and 18. So 4 kilograms of sugar, 18 grams of flavoring, and we'll find out what that minimum cost is. Here we have the original function, which is the cost of, in dollars, of producing a batch of the soft drink. So we have now our x value of 4, y of 18, and we substitute it into the function. And when we solve that, being mindful of our order of operations, we find that we have a cost of $1,336, which is the minimum cost to produce a batch of this new soft drink.